Alright, so we've had a brief introduction to magnetism, and we've begun talking about magnetic fields and magnetic forces. So I'd like to take a moment to talk a little bit in more detail about how the force between two magnets works, and then get a little more into the details of how we describe magnets and how you create magnetic fields. As I mentioned, we're not going to use any equations for magnetic force, but I still want you to know how the forces between magnets behave. So we've looked at several force equations in this class. We looked at gravity, the force between two things with mass. We looked at the electrostatic force, the force between two charges, and now we're considering the force between two magnets. Now, if you recall, the force of gravity looked like F sub g is g m1 m2 over r squared. The electrostatic force looked like k q1 q2 over r squared. And it turns out that the magnetic force, the force between magnets, F sub b equals something over r squared. Now I left that as something because there's not really one equation to rule them all. It depends on the context, and it's a bit more complicated. You really want to use calculus techniques to compute magnetic forces. So if you want to dig a little deeper, look up something called the Biot-Savart law, or reach out to me. We can get a whole another lesson in on magnetic forces alone. But the point is, the take-home point is that these are all inverse square laws, that they're all something over r squared. The separation, and particularly the separation squared, plays a role in how strong these forces are, and they all work the same way. And we talked about this when we brought up the gravitational force and the electrostatic force, that if something is, say, one distance apart and we doubled it, well, the force doesn't just go down by half. We square the effect of that separation. So if that separation is doubled, well, that's a factor of 2. We then square that 2, and the force would go down by a factor of 4. Similarly, if we bring things closer together, the force goes up, but not by the amount that we bring them together, but by the square of it. So if we have two things very far apart, we say get them 5 times closer together. The force doesn't go up by a factor of 5. It goes up by a factor of 5 squared. It would go up by a factor of 25. That is that inverse square law, inverse square law relation that we have discussed before. And really, what I want you guys to walk away from this course remembering is that all of these fundamental forces have that same inverse square law dependence. And there's a whole philosophic debate you could have about, why is that the case? There's geometry that could come into play, but some people like to take that as evidence that there is rhyme or reason into the fundamental laws of the universe. But we're not going to get into that today. All right, you may also be wondering why I called that F sub b. Well, it turns out magnetic field strength is represented by the letter capital B. And while we're at it, why not give some units to magnetic field strength as well? The units for magnetic field strength are Newton second per Coulomb meter. It is a derived unit that consists of these other fundamental units. And we actually have a special name for all of that stuff. All of that together becomes what we call a Tesla. That is the SI unit for magnetic field strength, the Tesla. However, Tesla is not what is commonly used because it turns out that Tesla is quite a large unit. So we also have the Gauss. And 1 Tesla is equal to 10,000 Gauss. Like I said, it's a big unit. It deals with large magnetic field strengths. However, there aren't many situations in which we are going to be dealing with magnetic fields that strong. So to give you a couple of references, a strong fridge magnet, one of the simple ways that you're familiar with magnets, a strong fridge magnet, one that you might have to really pull off that fridge with a little bit of force, that's only around 100 Gauss. That would be a fraction of a Tesla. And the most important magnetic field, probably to you or me, is the Earth's magnetic field. And the Earth's magnetic field, of course, it varies depending on how far away from the Earth you are. But of course, we're right at the surface. At the surface of the Earth, its magnetic field has a strength of around a half of a Gauss. I mean, that would be a tiny, tiny sliver of a Tesla. And that is why we use Gauss more commonly than Tesla. But Tesla is technically the SI unit. Gauss is the more practical one. And we're not going to be plugging these into equations, but you should know the words to describe these things that we're talking about. And Gauss is the word I would probably be using to describe the strength of a magnetic field. All right, well, let's take a break now and imagine what it was like to be someone who had no clue what magnets were before there were refrigerators to put magnets on even. As early as 500 to 600 BC, people were experimenting with lodestones, which is a name for a type of rock that's a natural magnet that has some iron minerals in it. It's got to have some iron minerals. That's really the key to being a lodestone. That gives it some magnetic properties. Turns out that iron's a special element when it comes to magnetism, and we'll come back to that later. But anyway, for thousands of years now, people have been familiar with some of the properties of magnets. They might not necessarily know why it happens, but they knew that it would happen. They knew that you could put a piece of lodestone, say, on a leaf in a pond, and it would align itself and point you north. And this was used for navigation, all kinds of things. However, the birth of modern magnetism and the study of magnetism as we now know it didn't happen until 1819. A guy named Hans Christian Ørsted accidentally discovered magnetic fields around wires while he was playing around with charge and current. And this led to the discovery that moving charge creates magnetic fields. And if you recall in our first video, that is what defines magnetic fields. Changing electric fields produce magnetic fields. And before we look at his setup, let me deal with some symbology here for a second. These are two simple symbols to allow you to draw three-dimensional directions on a two-dimensional piece of paper. So we can, of course, draw arrows up, down, left, right, but we need something for out of the page and into the page. And this little dot inside of a circle indicates coming out of the page. I was always taught to imagine like an arrow coming right at you. You only see the dot, so it's coming out of the page or at you. If we put an X in a circle, that is into the page. And if you could imagine shooting an arrow, you could see those fletchings, that X of the feathers on the back of the arrow going away from you. So the X in a circle is going into the page or away from you. So with that in mind, let's take a look at this setup of Hans's accidental discovery. So it probably wasn't exactly like this. This is nice and perfectly set up. But the idea is you have a wire, that's what I have in the center, that X represents current flowing into the page, and around it I've set a few compasses. And if you'll notice, those compass needles don't agree with each other. This one has north pointing right, this one has north pointing down, north pointing left, and then finally north pointing up. Well, which is it? Well, it turns out that north is what it always was, but your compasses don't see, or the Earth's magnetic field sort of gets lost in the strength of the magnetic field produced by the current. So that current flows into the page, and if you notice, there's a bit of a pattern to the way that those magnetic field lines point. If we go over to the right across the top, down on the right side, left on the bottom, up on the left, it looks like this magnetic field is flowing in a circle. And that is the case. It is flowing in a circle around the wire. Flowing current through a wire is how electromagnets work, and we'll talk about that. If we had gotten to do this lab, you actually would have created an electromagnet in the lab itself, a fun little experiment. But we can determine the direction of the magnetic field around a wire by what's called the right-hand rule. And you must use your right hand when using the right-hand rule. That is why it's called the right-hand rule and not the left-hand rule. You will get the opposite direction if you use your left hand. And the right hand rule goes like this. Your thumb is the current, and then your fingers curl in the direction of the magnetic field. So in our previous setup here, we've got our thumb being the current. It flows into the page. Our fingers curl around in the direction of the magnetic field. And sure enough, we have current flowing into the page and then a magnetic field swirling around in a clockwise manner. And it turns out that if you have a loop of wire, you can reverse the roles of your thumb and fingers in the right hand rule. It's all self-consistent. And I'll keep this actually handy just to point that out momentarily. So in that case, your thumb would represent the direction of the magnetic field, and your fingers curl in the direction of the current. So if we have current swirling around in a clockwise fashion, our fingers are the current, the magnetic field inside that loop would point into the page. That's my I as my current goes around, B into the page. Or alternatively, we can have I going counterclockwise, and then my B field, the magnetic field, comes out of the page. And it turns out that everything is completely consistent with our other picture. If we were to instead try to make the current our thumb still, that is still true. Our thumb can follow the current around, and our fingers curl around that wire, and sure enough, on the inside of that loop, the B field is going to be pointing upwards. What's not included is that on the outside, the B field would be going into the page, and similarly in this picture we would have a B field going out of the page. If our current goes around, it curls up, but on the inside of the loop, sure enough, it curls into the page there. So you can actually use either version of the right hand rule when trying to figure out directions of current or field, magnetic field, around a wire. And these effects stack. Magnetic fields are vectors, they add up, so if you stack up a bunch of loops, you can get a bigger magnetic field. And you see these coils of wire in inductors and solenoids. And we'll talk about that a little bit more. I would get to pass around some examples of these if we were in class. But we're setting ourselves up for some really cool stuff that I will cover in the next video. So we'll pause there, and then we're going to move on to Faraday's law, which is one of my favorite things in all of physics. So talk to you soon.